Welcome students. In this class we are going to learn about this more detail about on high level synthesis. Okay. So, in previous class we try to see, we take an example and show how high level synthesis can convert an C code into an equivalent register transfer level code. So, we try to formulate the problem each steps, right. What are the problems I am going to solve in every steps, and what are the challenges I am going to face in each stage, that I am going to talk about. And also I am going to talk about, give you a very high level idea how the common C constructs get mapped into the equivalent things in RTL. Okay. So, just to start with that, we have already discussed that C based VLSI design means I will start the VLSI design flow start from C code and then we will convert into RTL, and from RTL we will do this gate level transformation by logic synthesis tool, and from gate level to transistor level by physical synthesis tool and so on, and then finally we will get the chip IC after fabrication. But we will primarily focus on this high level synthesis because that is something is completely new in context of EDA design flow, right. So, the logic synthesis and physics synthesis part are kind of matured. So, the primary focus of this course will be on this C to RTL conversion by high level synthesis. Okay. So, we have already seen that high level synthesis is something convertants equivalent in C code into an RTL or register transfer level code, and it has come with a unique benefit like productivity, portability and permutability, right. So, productivity in the sense that it lowered the design complexity because you do not have to develop anything on RTL, you can write just a specification in C and you can actually completely get your IC quickly because you do not have to develop your RTL, right. And also, so the checking the specification correct or not will be done in the C level, which is much faster than the RTL simulation. So, you have this low design time as well as low design complexity, and it is a faster simulation, so faster verification. Okay. Portability is something, so we have a specification written in C, you can actually map it to FPGA, you can map it to ASIC, because the high level synthesis tool you can just set the parameter that I want to map it to FPGA or I want to map to ASIC and it will generate the RTL according to that, right. Even in the FPGA level you can have different vendors, right. You can have Xilinx, you can have Intel Altera and so on. Even for those FPGA have different components. So, you can actually target for a specific target boards, right. So, this is something give you the portability, right. From the same specification which is written in high level C++, you can actually make it to different targets, right. That is the another biggest benefit of high level synthesis. And then the permutability, which is basically the design space exploration. So, from the same specification, which is basically it's untimed, there is no objective, right, whether it is something for power, area or timing, nothing, is just a specific is untimed C specification, and I can actually explore different kind of design from the same specification. Here is a very nice example, that suppose I have a given very simple example of this, right, which is doing this the addition is basically in 1 plus in 2 plus in 2 in 3 plus in 4, right. Now, suppose I want to target it for reducing the latency, right. So, that means I want to do it very fast, right. And the corresponding data will be this, data path will be this, because there is no intermediate register. So, the latency will be 1, right, but it is the area is 3 adders, right. So, I can generate this RTL using high level synthesis, just specifying certain pragmas or certain parameters in the tool. Or suppose I want to optimize for area, so I can take this and I can convert this here. So, I can see here that I can actually take one adder and I am storing the intermediate results, and it's basically it will take 3 cycle to complete this 3 addition operation, because I have one adder, right. So, the area will be 1 adder, but there will be 2 registers also. So, the area will be 1 adder 2 registers, but the clock will be very faster, right. So, earlier it is 1 by T clock, now it is 1 by 3 clock, it is 3 times faster clock, right, because you are not the total delay of the combinational circuit is 3 adder here, here it is only 1 adder, right. So, that is the advantage, but it area is less, but it is slow, it will take 3 clocks, right. And then if you want to improve the throughput, that means you want to get your output fast, you will get a pipeline circuit like this, where you just still you are adding 3 adders, but it is in pipeline mode. So, that after one the pipeline stages are filled, you can get output in every clock, right. So, if you just suppose you want to do it for a streaming data, right, you are continuously giving the new set of data, you will get the output in every clock here, but here it is not like that, right. Here you will get it, but the latency is 1, but here the delay, the clock is very slow, but here the clock is still faster and you will get output in one clock. So, the point I try to make is that you can actually get all these three kind of data path just setting certain parameters in the high level synthesis tool, right. So, that is the kind of you can actually explore the design space using high level synthesis easily, right. So, that is the biggest advantage you have already talked about. So, let us now move on to the high level synthesis, and we have seen that high level synthesis consists of several sub steps, right. It is a complex transformation process. So, it goes through several sub steps like pre-processing, scheduling, allocation, binding and data path and controller generation, and then finally get the RTL, right. So, what I am going to do is that I am going to try to see what are the exact problem I am going to solve it here in every sub steps and what are the things involved there, right. So, that I am going to discuss in today's class. So, as I mentioned in the pre-processing step is something you have a C code, you convert into some intermediate representation, right. So, the task is like you actually identify the you break the big expression into 3 address form, you identify the basic blocks, you identify the control flow, you identify the data flow, and then you actually represent that input C behavior in that IR form, right. So, in terms of a control and data flow graph, right. This is what is happening here, and if you look into this compiler, because it is a C code, you need a parser, right. You need a compiler which is basically can parse a C code, right. So, and we have very common, we already know that GCC, LLVM. So, we can use any of such parser, because I do not have to write my own code, it is something, it is a C code, I can utilize the GCC or LLVM parser, which is actually parse this input C code. It will just do the syntax analysis, semantic analysis and give me the IR, and then most importantly in the IR level we can apply various kind of optimizations, which we will cover in some subsequent classes, that we can actually optimize certain things in the input code itself if there are some redundancies, and then finally that IR is something will represent in some form which understood by the high level synthesis tool. Okay. As I mentioned that there are some data flow analysis is involved here. So, there are information like a control flow analysis to be done. So, what is the control flow? We have to identify the package, we have to identify the loops, for that you have to do the dominator analysis, right. So, all those things part of this this compiler, right, and also we have to identify the data flow, the dependency among the operations within basic block and across basic blocks, right. You have to do this analysis for, as I mentioned, it is basically interprocedural if there are multiple functions, right. You have to do it for hierarchy of functions or within the function also, right, interprocedural also. Within the function what is the dependencies, and within the function you have some local dependency which is called basic block, right. So, we have already understood that. So, this all analysis involved in the pre-processing step. Okay. And at the output level what we understood that we actually get a basic blocks, right. So, we will represent our behavior as a set of basic blocks and their control flow, right. So, within the basic block what we have a sequence of 3 address operations where we have actually each operation consists of single operations, and it is a there is no control flow, right. So, this code is going to execute it top to bottom sequentially, right, and this is the control flow, right. So, after that you will go here, and once say this this particular condition does not hold, you will go to this basic block and so on, right. So, the pre-processing steps does all those things, and in the context of high level synthesis, since all the high level synthesis tool just have integrate one of the existing C compilers, say either GCC or LLVM. So, we will expect that our input is already converted into that 3 address form in terms of basic block representation. Okay. And in this particular course I am not going to go into detail of this, because this is very conventional compiler, you will get it in any compiler courses. So, I will assume that you have certain knowledge about that, and I will expect that whatever the input for my high level synthesis is after the pre-processing, right, where you will get the code in this form. And what I am going to do, I am going to take one basic block at a time, and then I am going to do the scheduling, and then we try to do the allocation binding, where we try to identify the minimum number of registers and function units which can be shared across basic block also, right, that we will discuss in detail in subsequent classes. Okay. So, now let us move on to the next step is something scheduling. So, we already know that scheduling is something where we assign timestamp to operation, right. So, what is my input? We have this input, we have this basic block informations, right. So, we have these operations, we construct a kind of data flow graph, right, DAG, the data dependency graph, right. So, which basically represent the dependency of operations, how the operations are dependent to each other, that is given to me, right. So, we will learn that it will be represented by a graph called sequence graph, okay. And then we have also the delay of the nodes, right. So, we have not discussed that in previous class, that these operations may not be always of single cycle, right. Some operation may be multiple cycles, some operation may be single cycle and so on. So, that information is also there, right. So, single cycle means it will complete this execution in one cycle, and if it is a 2 cycle operation, it will take 2 cycle to complete the execution, right. So, now that, so this is the called delay. So, for each node I know the what is the delay value, right, and then also I have certain kind of constraints. So, whether how much resource I can use or how much time I can utilize. So, those information also are there. And what scheduling does? It basically identify where the operation should start, right. So, the start time of the operation Ti for node Phi, okay. So, for each operations it will say when this operation starts. So, if it is a single cycle, it will complete the execution within the same cycle. If it is multi-cycle, it will start here, but it will complete in, after, so if it is a 2 cycles, say it will take 2 cycles, 2 clocks and all, right. So, this is something what schedule does. So, given this data dependency graph of a basic block and the delay information, it just say when this operation will start, right. So, this is what the tasks of the scheduling. But what are the complexities here? Let us try to understand this, okay. Say suppose I just give you a graph, some sequence graph or data dependency graph, and say you schedule it in 4 cycle, right. So, I give you this. So, here is the example. So, if you take that example, that DIFFQ example, you can actually schedule this behavior in 4 cycle, that we know, right. And now we will just say how many so I will just show you some possibilities, okay. So, this is what one of the schedule, where you see the main idea is that your schedule does not violate the data dependency, which I forgot to mention in here. So, you have to just find out the start time, but you may make sure that the operation data dependency must satisfy, right. So, this something must be maintained. It is not that you just assign timestamp, but you make sure that your data dependency is not violated, and whatever the timing or resource constraint given to us, that is also not violated, okay. So, now given a behavior, and say suppose I give you that you use only 4 cycle to schedule it, right. So, you can have many scheduling possibilities. So, I have shown 3 scheduling possibilities here, you see here. So, all are actually satisfying the data dependency. Here all this data dependency are satisfied. So, that satisfying data dependency in the sense, if there is a operation is dependent on the operation, so the previous operation must be executed, then only the dependent operation can execute, right. Otherwise, the data will not be available, right. So, data dependency will be violated. So, you see here I have 3 solutions here, which all take 4 cycles, okay. But here you see how many multiplier happening here, 4, right. So, that means there are 4 multiplier is going to execute in time step 1. So, that means I need at least 4 multiplier to do this. Here only 1 multiplier, 1 multiplier. So, there are 6 multiplication operation. There are 6 multiplication operations in this behavior, and I identify because of this schedule, since there are 4 operations schedule is 1, I need at least 4 multiplier, because these 4 will run in parallel, right. So, what does it mean? 6 multiplication operation need 4 multipliers, okay. And if you look into this 4 multiplier, only 1 will be used here, 1 will be used here, and none of them will be used here. So, that means in this particular clock 4 multiplier will be utilized, and rest of the time most of the multiplier will remain idle, okay. So, this is one solution. So, remember these are all valid solution, because it does not violate the data dependencies, okay. And now see, this is another solution. Here there are 3 multiplier scheduled here, still it is 4 cycle, right. This is also 4 cycle, this is also 4 cycle. So, here because 3 multiplier is in parallel here 2 and it is 1 here. So, it will take at most 3, basically 3 multiplier to execute this, right. So, both are 4 cycles, both has 6 multiplications, it need 4 multiplier, this needs 3 multiplier. So, let me take another solution here. Here 2 multiplier is scheduled here, 2 multiplier scheduled here and 2 multiplier scheduled here. So, I need 2 multipliers, right. This also take 4 cycle and this all 3 are valid solution because it satisfy the scheduling constant. So, this give you a very classic example that given a timestamp also you can have many scheduling possibilities, at not necessary that all possibilities will give you same resource, right. I have a very nice example here that I have taken on behavior where there are 6 multiplication operations. I show you 3 schedule and all take 4 cycles, 4 clock cycles, but this is the best solution in terms of resource because it can do it in 2 multipliers, right. So, basically the point here is that in the scheduling given some even the time limit, that time constant say 4, there are many solutions, right. You have to develop some algorithm that will actually able to identify this solution, right. This is something the better solution other than, right. So, that means for your scheduling problem is not only identifying a valued solution, but a optimal solution, right, or a good solution, right. So, that is something is going to happen in during scheduling. I do not, this example does not give you another angle of this problem, right. So, which is basically here I told you this 4, right. So, I just mention you that it is 4, but if I do not mention that, right. So, if I say I told you that I give you 2 multiplier, you identify what is the minimum time required, right. So, that means you might maybe do it in 4 cycle, you may do it in 5 cycle, you might do it in 6 cycle, but you have to identify the solution, the 4 is the best solution, right. So, given 2 multipliers you might have many solutions which might take 4 cycle, 5 cycle, 6 cycle, 7 cycle, 8 cycles, but you have to identify that for given a certain resource bound, this is the best time I can obtain, right. So, that is another angle of the problem. So, in that way there are 2 kind of problems we can look into this scheduling, which is called minimize latency under resource constant or minimize resource under latency constant. Okay. So, these are 2 conventional dual problem, because if you just try to use minimum resource, your number of clock will increase, right, because the operation has to be scheduled in more time, right. If your number of resource is less, you need more time, and if your resource is more, you need less time, right. So, these are the 2 conflicting requirement. So, usually in the scheduling, the 2 problems that we want to solve is that I tell you that this is my resource constant, you identify the minimum latency you can achieve, what is the best latency you can achieve using this resource, right. This is one kind of problem we are going to solve. The other kind of problem is that I have given you a latency bound, just like the example I have shown here, that let us you schedule this in 4 cycle, but you identify the minimum resource, right. So, this is another angle of the problem. So, both are important problem and we are going to discuss the kind of efficient algorithm to doing that, right. So, so that is about the scheduling. So, let us move on to the next phase. The next phase is allocation and binding, and we have already understood a high level that allocation means you have such set of operations, you have to map those operations into function unit, because in hardware your operation is executed using some function unit, right. So, the operation to be mapped to the function units, and the variables of your program map to be registers or RAM memories, right. So, you are going to map to the memories. So, this problem is here, you have set of operations, you can utilize the same number of resource, which is okay. Say if there are 6 multiplier multiplication operation example here, you can always utilize 6 multiplier function unit, multiplication unit, but it is not good, right. So, I can show you that in this particular example I can actually utilize 2 multiplier, because at most my requirement of max multiplication in every state is 2, at most 2. So, I need 2 multipliers, right, and I can put this multiplier into multiplier 1, this into multiplier 2, this into multiplier 1, this into multiplier 1, this into multiplier 2 and this multiplier. So, this will not create any problem, right. This is what is the resource sharing, which is very important in the context of hardware, because I do not want to arbitrarily use a random number of hardware, because that will increase my area, increase my power, increase my time, anything, it will all increase, right. So, I have to always look for using minimum number of resource, right. So, as I mentioned in this example perfectly that although there are 6 multiplication operations, 2 multiplier is sufficient, and I can actually share one multiplication function unit for this 3 multiplier operation, and I can use another multiplier function unit to share these 3 multiplication operations, and that is what is important, and that is what is being done in the allocation and binding phase. So, from this schedule I identify that 2 multiplier is sufficient. So, that is my allocation. So, I allocate 2 multiplier for this problem, and then I bind these 3 operations, this V1, V5 and V6 into multiplier 1. So, this is the binding of this operation to the multiplier, and I am binding V2, V6 and V9 into multiplier 2. So, that is the binding of the operations to the function unit. So, we understand that this allocation and binding. So, you identify the minimum number of resource for a given schedule, and you understand that for different schedule your resource minimum resource requirement is different. I have already explained in that example, right. So, you identify for a given schedule what is the minimum resource needed, and then you bind them, right. So, during bind you make sure that there is no, the operation that are running parallel should not be bind into the same function unit, because you can at a time you can only execute one operation in one function unit, right. So, that is what is about this allocation and binding of operation to the function units. The similar proceeding has to be done for variable to register binding, right. So, you have many variables in your program, and you want to map those variables into registers, because in the hardware you do not have variables, you have to store them in some hardware unit sequential element which is registers, and you have to do that. Again, if you have to set 10 variables, you can always map them into 10 registers, but that is again not the good idea, because I want to utilize the resource, right. I do not want to overuse the resource, and the basic idea here is that in C program whenever there is a variable, we never thought about their lifetime or when this is getting used, right. So, it is not that one variable is need for the complete program, right. So, you define a variable, say here v equal to something, and then say this is the last time where you are using, say for v5 equal to v plus something. Okay. So, this is line number 1 and this is line number 12, and say the code complete program is 15 lines. Okay. So, that means I need to store the value of the variable during this time. Okay. So, I do not need to store this after clock level 12, because after that the v value v never be used, right. So, if there is another variable, say v6 is defined here and it is getting here. So, I can actually store this v6 and v into a single register, say R1. Okay. This is what is the way I am going to identify how many registers I need. So, if there are 2 variables which is not getting used in the same time, or that means or their lifetime is not overlapping, I can put them into same registers, and that is how the sharing happens. So, this is how you identify how many registers you need to be allocated for these variables, and then you bind them. This is what the binding I have done, that v register v and v6 map to register 1. Okay. So, this is what register allocation and binding. We will go into more detail here how this mapping happen and what kind of algorithm to be done. So, you have to always keep in remember that whatever I am talking about scheduling, allocation, binding, this is not a manual job, right. We need a software which is going to do that. So, the most important part here is that how can I automate this process, right. I identify this, but can I write a program that will automatically identify the lifetimes of the variables and then identify the variables which has non-overlapping lifetime and map them into same registers, and you have to guarantee that this actually always result in minimum number of registers, right. You can have many such mapping, but can you identify what is the minimum number of register needed, right. Similarly for FUs. So, these are the interesting problem that we are going to solve during this this course, that I am going to talk about different algorithms that I am going to do these things. Okay. Once this allocation and binding happen, the next phase is kind of conventional but important, that you have to make the data path, right. You have the how many function units are there, how many registers are there. What you have to do, you have to make a connections, and this connection is that because this FU is getting shared or it is basically performing multiple operation in multiple time step, their input may be different, right. So, it may be that one FUs in the register. So, its input for this FUs is R1 and R6 in time step 1, and say R2 and R1 in time step R2 and R1 and R5 in timestamp 3 and so on. So, these are the possible inputs are coming to these registers to this function unit, right. So, how to make this connection? You have set of registers. So, you have to put some kind of multiplexer here, so that you can actually give these inputs and you can actually do a time division multiplexing, right. It is not that all values will come in same clock, rather in every clock one of the value will come and I know which value will come in which clock. Accordingly, I can give a control signal here, which will make sure that in the timestamp 1 only R1 should come into FU among all these inputs. Similarly, in timestamp 1 R6 only come into the FUs in timestamp 1. Okay. So, this is how the interconnection to be made, right. So, you have to identify for FU what are the possible values is coming to this, and you make a connections, and you also make sure you add a proper control signals, and then in that particular control state you give that particular value, so that R1 should come, right. This is what is the data path and controller generation, right. So, the controller is, once the data path connections are done, you identify what are the control signals you need for FUs, ALUs, for marks, for register inputs. So, everywhere there are control signals and you have to control the data, right. So, you have say 10 registers, but may not be all 10 registers get updated in a clock, right. So, only say 3 of them gets updated in a clock. So, we have to make sure that in that particular state only in a write enable for those 3 registers are 1 and for rest of the things are 0. Otherwise, it will store some garbage value will come into those registers, right. Similarly, as I mentioned for the data path, if there is a marks which has 4 inputs to FU, you have to make sure that in clock 1 what are the value I should set, so that the corresponding correct register value will come into FU input, right. This is what is the controller synthesis, that every state you identify what are the operation to be performed, and accordingly you set the control values, control signals to 1 or 0 properly, so that exactly required operation going to be executed in that times, and rest things are not going to happen in that state, right. This is what is the data path and controller synthesis, and this in this particular part what is important is that how to identify these things automatically, and what will be your interconnection type. It can be bus based or mux based, right. So, we will go into all detail, but this step you can consider is kind of more conventional, because the most of the decisions already taken during allocation and binding phase and scheduling phase. So, this is where you have to make sure that whatever the decision has been taken in scheduling, allocation and binding is going to happen properly in the hardware, right. So, that is something is the interconnections ensured, right. So, that is going to happen in these steps. Okay. So, with this, if you just follow all these steps, finally you will get an RTL which is have a separable data path and a controller, right. So, you have a data path is going to execute the operations, and you have a controller which is nothing but a FSM, finite state machine, where every state it assign this 1-0 signal and give that value to the data path. As a result, this proper operation is going to execute in the data path, right. And in some state, if there are some conditional operation happen, so the value of that conditional operation also return back to the controller, right. So, suppose you are doing A less than B. If A less than B, then you are going to happen some operations. If A less than B is false, then you are going to do some operations, right. So, that information must be come back to the controller, so that controller understand what operation to be done in the next state, right. So, that something come back to the controller. So, once you have done that, so your data path will looks like this, your controller will looks like this, and in combination this will the RTL which will execute the input behavior that you have given to the high level synthesis tool, right. This is what is the automated conversion process, and as I mentioned in this course I am going to look into the algorithms that are going to do the scheduling, the algorithms that are going to perform this allocation binding, and the operation or the kind of algorithm that can actually automatically synthesize the data path and the controller. Okay. So, that will be a major portion of the course, and which I am going to follow from the next week. But in today's class I am going to give you some interesting fact that in the C++ there are different construct, like you have functions, you have operations, you have variables, you have arrays, you have a control flow. How those things is going to map into RTL in general by high level synthesis, right. What is the corresponding things in the hardware, right. That is something I will just give you a brief idea, and obviously again I am going to take each of them in detail, and how efficiently they are going to map to hardware I am going to discuss. But here I am just give you some high level idea that the common construct of C, what is the equivalent things in hardware. Okay. So, the first thing is the function. So, you just know that the function gets mapped to module. I mean, I am expecting that you have some familiarity with the Verilog or VHDL or HDL language. If not, please go through that, otherwise you might face a little bit struggle in the latter part of the course. Okay. So, the function gets to module in the hardware. The module is a kind of a component where you can do perform specific task, right. The argument of the function become the IO port for the module. Operations mapped to the function unit that we have already discussed. Scalar or the variables gets mapped to the wire or registers. We will identify, we will talk about which is wire and which is register. The arrays map into memories, RAM and ROM, and control flow is the control logic of the FSM. Okay. This is the general mapping. So, I will just talk about them briefly before concluding today's class. So, as a function, so function become a module, right. So, you have the top level function. So, the top level function become top module, right. So, this is the module that is the RTL I am going to generate, and whatever the input of this top level function, those will become the port of this, right. So, suppose this top has input say x and y and it is producing out. So, it will create x and y as input and it will produce out as the output. So, it will create two input port for x and y and one output for y. Okay. Most importantly, it actually generates the synchronization signal. Okay. So, it is a x valid and this is y valid, right. So, you have whenever this value you give valid equal to 1, then only whatever the data you are giving is a valid data and this tool this RTL will take that, right. This will be useful for synchronization, because if once you create this module and if you want to integrate into a bigger SOC, you need the synchronization when this data the valid data is coming and when this particular module is creating a valid output also, because it may not give you always correct input, right. So, if the latency of the circuit is say 4, so every 4th cycle it is going to give you a correct value, right. So, this something has to the synchronization things is already maintained. Okay. So, whenever there is a function, it create a module. So, for example, in the top if you have a function called a and b, it will create a module A which will implement this function A, it will create another module which will implement B, and then this function will be invoked by instantiation of the module in the top level, right. So, in the top level I am going to instantiate this module A and module B, and I am going to connect with the proper control signals, so that control signals and the values, so that operation A actually can perform the desired operations. Okay. And it can actually maintain the hierarchy also, right. So, if this B again calling a function C, it will create a module and it will be instantiated within the modules B. Okay. So, in general it will create a hierarchical RTL modules, so which will maintain the hierarchy structure of the original C code. Okay. But if sometimes the function is very small and it might be inline also. Okay. So, so it might get inlined in between. Okay. So, as I mentioned that the function arguments, so the function argument become the port. So, here is the example that in1 and in2 become the port and out is the output port, but it also have the valid signal. So, that this whole process can be integrated in a bigger system, right. So, this particular valid signal automatically generated by high level synthesis tool. And just to give you the idea that if this particular take is taking say 4 cycle, as I mentioned earlier also. So, it is not that you can give input in every clock, right. So, it will take input in every 4 clock. So, you have to, so whenever or it will wait for the valid signal, whenever the valid signal on, then only it is going to take it. And now, if the valid is coming less than 4 cycle, it will ignore that input, because it cannot take in the input once it is taken in next 4 cycles, right. So, this is what is the idea, and whenever it produces a correct valid output, it will just say okay, this is the output is valid, and you can integrate into a bigger system which may have some different module which might take this as a input, and say there may be some another module which might produce these inputs, right. So, this will actually combined or you can actually integrate together, and so that it will work perfectly, right. So, that is what this argument becomes, and usually high level synthesis tool generate all these valid port as well, okay, for each inputs. And the expression I have already explained that it will map to these function units, and usually the expression gets splitted into 3 address form that I have already discussed, and then it gets scheduled, right. So, it is not that the whole expression is going to execute in one clock based on the target clock period and all. you might try to execute this in multiple cycle, that already I have discussed. So, here is the example that you have, so this in first clock, this is my clock 1, this is my clock 2 and this is clock 3. So, this operation is going to execute in 3 clocks and the intermediate data will be stored in registers. Okay. This is a pipeline implementation, but you can have different implementations for that. Okay. So, the expressions gets into function unit, and how many time it will take to execute an expression depends on the target clocks and the resource availability. Okay. Arrays map into RAM and ROM. If it is a read write array, it will map to RAM. If it is a constant array, that means only read only array, it is going to map to ROM. Okay. So, basically this array maps to RAM, and the interesting is that index become the address for this, right, for the RAM. And one important things to be noted in the hardware, that this array now once you map this into RAM, it has different other signals, right. So, it has that this address, in which address you want to access, it has some read enable signal whether you want to access this RAM or not, and there is a write enable. So, whenever you want to write something, you have to give this write enable equal to 1, and you have to give this corresponding address and the value which you want to write, and then the data will be written to RAM. Okay. And similarly, once you read something, you give the address, you give this C equal to 1, write enable equal to 0, and the corresponding value will come into A out. Okay. So, this is how this access is going to happen, but in the hardware this RAM is not exactly like arrays, so that you can access any content at any time. Rather, in the hardware this RAM will be accessed using ports, right, either it will be a single port or dual port. So, that create lot of bottlenecks, and I will put a significant portion of this course time to talk about that. That it is not that if you have say 10 access to array in a expression, you can do all this 10 access in the same clock, because that does not support in hardware. So, you have to come up with some strategy so that you can actually perform that operations, either you do it in multiple clock or you rewrite your code such a way that that can be doable. Okay. So, we will talk about all these things in detail in this course. So, loops in by default it is a ruled implementation, that you have this loop. So, it will create a one body of the loop and it will get iterated for n times, right. So, this is called iterative implementation or rolled implementation. If one iteration takes say 4 cycle and it is say n times loop, so it will take 4 into n clocks to complete that implementation. Okay. So, other than the loop can get unrolled. So, you basically unroll the loop and you remove the loop and you make it like this and you execute in the hardware, or you can actually do a pipelining, and the pipelining is one of the most important optimization in high level synthesis, that you basically assume that you have a implementation of the loop and then you actually run different iteration of the loop in parallel, right. So, basically you add some pipeline stages and then you actually start this iteration 0 here, and the next time you start the iteration 1 and you have pipeline stages in between. So, basically different part of the stage of pipeline perform the operations for different set of inputs, different iterations, right. This is what the loop pipelining is, very important optimizations, and as a result you can actually execute the loop in order of n times if the number of iteration of the loop is n, okay, which is very interesting, and I am going to talk about in detail in the this course. But in general this loop is very important because it takes lot of time. So, you must have an efficient implementation of the loops in the hardware, right. So, again we are going to discuss about this loop things in detail in subsequent course. Okay. So, with this I conclude today's class, and from next week I am going to talk about these scheduling problems. Okay. Thank you.